Hi there again, people. Solomon Saduma. Thank you guys for watching these videos. We are going to now continue with a discussion on implied domain. In the last video, video number 7, we looked at the implied domain for square root functions. In this video, we will look at implied domains in the case of reciprocal functions, okay? First of all, we will want to understand what we mean by the reciprocal function. So let's start on the video straight away. What are we going to be looking at? What do we understand by a reciprocal function? What is a rational function? Are the rational function and reciprocal functions related? If so, how? Okay, we'll look at that. 2, we will look at the effect of the denominator on a ratio. A ratio is a fraction, okay, where there is a numerator and a denominator, okay? Then we will look at the indeterminacy rule, or an axiom on rational functions or reciprocal functions, all right? What we mean by indeterminacy. Number 4, we will look at the implied domain for reciprocal functions. And after that, we will sketch reciprocal functions, right? Just in the same way that we were able to sketch square root functions, we should also be able to sketch reciprocal functions. By this time, we will have known what we mean by a reciprocal function, so sketching them should be straightforward. Number 5, we will then, because we will have known how to sketch the reciprocal function, we will be able to determine the range of our reciprocal function given the implied domain. So once we have the implied domain, we can come up with the range for the reciprocal function. And after that, of course, as always, we will look at some questions together, but I will also put some for you to try, okay? So worked examples and sample problem set for you to try out. Let's get on with it then. The reciprocal function. Here is a definition. A reciprocal is referred to as the multiplicative inverse of some value. So like to say, the reciprocal of 2 is 1 over 2. So you invert, the use of the word inverse can sometimes be confusing, as we will see later. But basically, the reciprocal of 2 is 1 over 2. The reciprocal of 1 over 2 is 2. So you take the number and flip it, and that is the reciprocal. So by definition, the reciprocal of a value, a number, or a function, or a variable, its reciprocal is 1 divided by that variable, okay? For example, the reciprocal of b is 1 over b. And the reciprocal of 1 over b is b, okay? All right, so the value of b could be a number, so it could be a 2, a 5, a square root of 3, all right? But it can also be a variable, x, or y, or z, or it can be a function. So it could be 1 over f of x, 1 over h of x, and so on, okay? Good. So if y is the reciprocal of 2, then y must be 1 over 2, okay? I hope you got that. Here are other examples. If we have, so writing 1 over the square root of 1 minus x, well, this is the reciprocal of the function, the square root of 1 minus x, okay? Secondly, another one, perhaps, yes. So 1 over x squared plus 4 is the reciprocal of x squared plus 4. Similarly, x squared plus 4 is the reciprocal of 1 over x squared plus 4. I hope you've understood what we mean by the reciprocal of a number, or of a function, or of a value, okay? So the second definition is for rational function. So a rational function is any function that is a ratio of 2 polynomials. So if you remember what polynomials are, so 1x, or let me write it like this. So a polynomial can be expressed, so let's work with the polynomials that you know. So x squared plus 3x plus 2 is a polynomial, and we say the degree of the polynomial is 2. X, or 5x plus 3, is a linear polynomial. The degree of x is 1. The highest power is called the degree of the polynomial. Okay? Somebody could argue that 5 is a polynomial because it's 5x power 0, except that we normally say that n should not be equal to 0, where n is the highest order of the polynomial. Okay? All right. Either way, for it to be a rational function, the two functions in the numerator and denominator should be polynomials, although the numerator can also be a constant, so I can write 5 over x. The denominator is a linear polynomial, or x plus 1. This is a rational function. I can write 5x over 3x squared plus 4. Both numerator and denominator are polynomials, and that makes this a rational function. So rational functions are made up of two functions, one in the numerator, g of x, and one in the denominator, h of x. Okay? So here is a small difference between a rational function and a reciprocal function. Okay? So the reciprocal function can take any value really, like we said. So if I write 1 over e power x, this is a reciprocal function, but it is not a rational function because e power x is not a polynomial. Okay? Okay. Now we can move on. So our task now is to reason with this polynomial. So this is a rational function and the other one is a reciprocal function. Let's do some investigation here, investigating the reciprocal function. We will be looking at the behavior of y, so the value of the function, as we change the value of x in the reciprocal function given by this. So if this is a reciprocal function, what happens to the value of y as we make the value of x, as we change the value of x? And in this case, we are going to make the value of x smaller. So what happens to the value of y as the value of x gets smaller and smaller? All right, so let's do this. I have put a graph here. We're going to fill in that graph. Okay, and I also have a table somewhere here that we are going to fill up. So the values of x we'll write there, and we'll write the values of y in the second column. So when x is 1, we put 1 here, right there. So y becomes 1 over 1. The result should be 1. Okay, and so we can plot the coordinate of the point 1, 1 somewhere here. So if we plot the coordinate, there it is. Okay, all right. What if I use 0.5? I'm making x smaller and smaller. I want to see what's happening to y. So if x is 0.5, if I make x 0.5, put 0.5 there, 0.5, 1 divided by 0.5 is 2. I hope you know that. You can check on your calculator if you must, all right? Because it's 1 divided by a half, so 1 over 2, so the 2 goes up, all right? So it becomes 2. So if x is 0.5, y is 2 there, okay? And so if we plot the coordinates of the point 0.52, so 0.5 is somewhere there and 2 is somewhere there. There we go, all right? So the value, when we make the value of x smaller, the value of y has increased. You can see that. All right, I'm going to make the value of x, I'm going to reduce it to 0.2. If I make it 0.2 and put 0.2 here, this is going to be 5. 0.2 is 1 over 5, so the 5 goes up and the result is 5. So when x is 0.2, y is 5, so we go and plot the coordinates of the point 0.25, and that should be somewhere there. Already I can see the value of y is becoming bigger, and in fact here it jumped by 1, but now here it's jumped a little more. What about when x is 0.1? Substitute 0.1 here. We get 1 divided by 0.1, and that is 10. So 0.1 is to 10. So I come for 0.1 here and plot, and we can see the number has jumped even further, right? So what we are saying is that as I increase, look at that. If I put 0.01, I'm reducing the value of x now to 0.01. The value of y is now 100. I can't plot 100 here, but I know that it is way, way up there, right? So, therefore, the value of the value of y has really shot up to 100. From 15, we've gone all the way to 100. And when x is 0.01, I've made it even smaller. Put 0.01 there, I expect 1,000, and that means my value of function, so that's now 1,000, the value of my function has even gone further up, okay? Really, really goes much further up, all right? So you can see that as I reduce the value of x there, the value of y, what do you think happens to the value of y? Must go even further up. This must be much, much bigger. Okay, so as I reduce the value of x, the value of y becomes bigger and bigger. Now, I've made the value of x a millionth. Okay, if I substitute that there, I should get 1 million. So the value of y is going to be at 1 million. So clearly, as the value of x is approaching 0, getting smaller and smaller, the value of y is getting bigger and bigger and much, much, much bigger. So that the question is then, what happens if eventually I'm going to put a 0 there? What's going to happen? Well, we do not know what happens when we put a 0 there. In fact, the number is probably so large that we do not know about it. And in mathematics, when we do not know anything about a number, we refer to it as being indeterminate. It is undefined. And we use the symbol, the sleeping 8, to represent an undefined number and refer to it as infinite, all right? So the number is going to be so large that we do not know anything about it. When we don't know anything about a number, if we can't explain it, if we can't use mathematical axioms or mathematical rules to explain it, we say that it is undefined and we avoid it, okay? All right, so the result gets exceedingly or infinitely large that we cannot claim to actually know anything about it, and for that reason, y is said to be undefined when x is 0. The y does not become 0, as you have seen. It gets really, really large, but so large that we don't know what it is, so we say it is undefined, okay? When it is undefined, we use the symbol there, okay, for infinity, all right, and write that when x is 0, in other words, 1 divided by 0 is infinite, okay? Undefined. So we do not know anything about it. So if this becomes a 0, we will know nothing about y, and we say y becomes undefined. We don't want anything to do with a function that we cannot define as mathematicians, okay? So now we know that. Let's move on. Let's move on to the next part. All right, so based on that little observation there, if any ratio r is such that r is a over b, where a and b are real numbers, like 2 over 3, 2 over 5, or whatever, then for a value of b equal to 0, if b is 0, our ratio becomes undefined. We will not know anything about it, all right? So for this ratio to remain defined, the value of b must never be equal to 0. And this is the rule that I want us to keep in mind, okay? So whenever you have a rational function or a reciprocal function, the denominator there must never be equal to 0. If it is 0, that whole thing becomes undefined, okay? So a function f of x, so if we are given a function f of x is 1 over x or 1 over h of x or whatever, this thing in the denominator here must not equal 0, okay? And this is the rule that we are going to use to determine the implied domain for reciprocal and rational functions. Okay, I hope you got that. So the reasoning, also based on axioms, is that the denominator must not be 0 if this is to remain a function that we have defined, that we can define. Okay, so if f of x is a defined function, is a function that we know, If f of x exists in the domain that we know, then that domain must not include 0 inside it. Okay, so that denominator cannot be a 0. Okay, so let's see. Let's use that rule. So this is rule number 2. Remember rule number 1 relating to square root functions. So rule number 2 will relate to reciprocal functions. And it says, for a reciprocal function to be defined, it must have a non-zero denominator. So the denominator must be a non-zero for it to be a definable or defined reciprocal function. Let's use that then to determine, let's use that rule. We can use this knowledge to find the values of x for which the function y is defined. So for which, remember the function we were looking at, the reciprocal function. So we can use this idea to determine values of x for which a reciprocal function is defined. In other words, we can use this rule to find the domain of the reciprocal function. As a matter of fact, the implied domain of rational or reciprocal function. Okay? Here is a worked example. Find the implied domain and range of the following reciprocal functions. Okay? Here is one. What is the domain and therefore range of this reciprocal function? A second one is going to be that. Okay? What's the domain and range of this reciprocal function? If you remember your transformation, for those who've done transformation, if we want to map this onto this, which transformation maps this function here onto this? Well, this is simply a translation. The graph moves that way 2 steps, all right? But first of all, we need to know how this graph looks like before we move it 2 steps in that direction. Okay, so this is A and B. We're going to do this now. And there is C, all right? What is the implied domain of this reciprocal function? And lastly, what is the implied domain for number 4 there? That reciprocal function containing a quadratic function, quadratic expression in the denominator. Okay, let's see. We'll start with the first one. So I'll keep the question here. Find the implied domain and range of the following reciprocal function. So we'll start with the first one here. Okay, so we go back to the rule number 2 that we just came up with, that if this reciprocal function is to be real, to be true, or to be definable, the denominator there, and this is the argument of a reciprocal function, all right? That argument, that denominator needs to be, must not be a 0. Can be anything but not 0. So we will say that x has to be anything but not 0. So by rule number 2, the denominator must not be a 0. So we'll write x cannot be 0, all right? And if x, by just writing that, we have already stated the implied domain, except we have to write it in set builder notation. Okay? Hence, the domain is everything in the real number line other than 0. And we write that as x is all numbers in the real number set other than 0. 0 is in the real number set, but we will take out 0 and everything else will fall in the domain of this reciprocal function. Okay? Now, if x cannot be 0, we call line x equal to 0 as the vertical asymptote. But we can talk about asymptotes later for those who've not heard of that term before. Okay? So when we draw the graph, this is how it looks. This is the graph of this function. You can try sketching it on your graphical display calculator. And this is how the graph looks like. So clearly, as the value of x becomes bigger, the value of y becomes smaller. On the other hand, as the value of x becomes smaller, the value of y becomes bigger. And this is true on both sides because x can be positive or negative, like that. Okay? Now, so the line x is 0 is an asymptote. Line x is 0 is the y-axis, which is to say that the graph cannot cross the y-axis. Okay, that's why we say the graph is asymptotic, all right? to the y-axis on either side, like that. All right, so while we are at it, we've already determined the domain. What do you think the range of this reciprocal function is? Okay, you can pause the video and try it out. Okay, but otherwise, the range of the function is anything that is not 0. So the value of y, this graph is also approaching 0, but never really touching the x-axis. So x has to be greater, y has to be greater than 0, and y has to be less than 0. So anything below can be a value of y, and anything above 0 can be a value of y, and but not 0. So we will write from the graph, the range is y is real, such that y cannot take a value of 0, and of course we need to put the squiggly brackets here and here because it has to be a set in set builder notation, like that. Okay? All right, let's look at the next one. I think I left one for you. Worked example, here is the second one. All right, if this function, for us to find the implied domain, we reason just like before, rule number 2, the denominator there, the denominator is x plus 2 now, not just x, but x plus 2. That denominator must not be 0. So we reason from that rule that x plus 2 cannot be 0. Move the 2 to the other side, which means x cannot be negative 2. All right? And that there is the domain. So the domain is anything in the real number line other than negative 2. And we write that, okay? We write that in set builder notation as x is all elements in the real number set, but x cannot be negative 2. All right? We can sketch that graph. All right? If we sketch it, it looks like that. You notice that it's just like before. The original graph, 1 over x, was going about the y-axis. It was lying around the y-axis. The y-axis was like the the line of symmetry, rotational symmetry, as a matter of fact. But now you can see this has moved 2 steps this way. So there is actually now an asymptote. Instead of the asymptote being the y-axis, it's now somewhere here. All right, because x can now not be x cannot be negative 2, as we have seen, right? X must not be negative 2 because negative 2 is a vertical asymptote, right? And so this is where we are going to have our asymptote right there, okay? And the range is still the same. The values of x can be anything, values of y can be anything on the y-axis except y equals 0. All right? Okay. So here is the last question. Second last question, as a matter of fact. F of x is 1 over 4x minus 1. All right, once again, find the implied domain and range of the following reciprocal functions. So again, by rule number 2, the denominator must not be a 0. So the 4x minus 1 cannot be a 0. So we write that 4x minus 1 is not 0. If we rearrange that formula, 4x minus 1, move negative 1 to the other side, we get 4x is not 1, in which case divide by both sides by 4, and we get x cannot be 1 over 4. This also would mean that 1 over 4 is the vertical asymptote, right? Okay, and so given that, we can, as it is, this is indeed, it's the vertical asymptote. It is also the implied domain, all right? So writing that in set builder notation, we would simply say x is real and x cannot be 1 over 4. All right, now I've sketched this graph in a different way. If we're going to do this, we put a y-axis, an x-axis, and remember that x cannot be 1 over 4. So we go to 1 over 4 there and draw a vertical asymptote. All right, that's 1 over 4. And then the reciprocal functions, as we've already seen, will revolve around that vertical asymptote there. So we have the lower end and we have the upper end. We can determine the y-intercept there, right? Because x there is 0. So at the y-intercept, the value of x is 0. So we can replace 0 there, all right? And we end up with the -1. 1 divided by -1 is -1. And so the y-intercept is -1. Having determined this, it is now possible for us to talk about the range of this particular reciprocal function, and we can see that all values of y are acceptable except the value of y equals 0, which is also to say, by the way, that the line, the x-axis is the horizontal asymptote. So line y equals 0, which is the x-axis, is the horizontal asymptote there. Okay, so the range is all values of y other than y equals 0. I did not remove this here. This is not there. So all values of y except y cannot be equal to 0. All right, let's move to the next. All right. Right, this is, I think, the last one. Now you notice that the denominator there is quadratic, right? So once again, using rule number 2, we can say that x squared minus 5x plus 6, that denominator, must not be 0 if this reciprocal function is to be defined, right? So what values of x, the values of x that will make this a 0 are not allowed. Okay, so how do we find that? We factorize where possible, and if we were not able to factorize, we can use the quadratic formula to find those values of x that will make this a 0, and those will be the values we don't want. They will be the exclusions in the domain. So in this case, it's very easy to factorize this. This is, I think, x minus 2, x minus 3 equals 0, and from here we can easily see that if I make x a 2, the whole thing is rendered as 0. So 2 is not accepted in this domain. Similarly, if I make x a 3, that renders the left-hand side 0. So a 3 is not acceptable in the domain. Hence, the domain is everything other than 2 and 3. All right, we can write that in set builder notation and say x is all real numbers such that x is not 2. All real numbers except x cannot be 2 or 3. Okay, let's sketch the graph. Now, because there are 2 disallowed values of x, it also means we have 2 vertical asymptotes. Okay, so let's sketch this y-axis and x-axis. We have 2 vertical asymptotes at x is 2. In other words, x is not allowed at 2, so it is an asymptote, vertical, and the same as 3. So let's put those through. So at 2, there is a vertical asymptote. We have another vertical asymptote at 3. All right, this is a sketch, so these positions need not be perfect, all right? It might be that this distance here is not twice this distance, but it's not important, okay, because we are sketching. All right, and so what we have, as we would expect, one line will come from the left and go up because the value of the function increases below 2. All right, we can also find that y-intercept. The y-intercept is x is 0, so substitute that there, and we get 1 over 6. So this must be a sixth. Okay, 0.11 something, 0. Right, whatever. Okay, so that's the y-intercept there. The next part will be in here, and if we sketch that, it looks like that. All right, and we have that, and there is a point here whose coordinates we need to know. Okay, which turns out to be 2.5, exactly in the middle between 2 and 3 for the x-axis. X coordinate. The y coordinate there is at -4. Okay, you can find this out once you sketch this on your graphical display calculator. And now, because we have that, we can determine the range. We know that values of y can come from negative infinity all the way to negative 4. Negative 4 is included. And after that, y is not allowed until we get to 0, and it is above 0. So values of y, therefore, the range is given by y is all real numbers except, and y lies between negative infinity to negative 4, and again from 0 to infinity. Of course, we need to put brackets here like that, right? Another one here like that. In set builder notation, the notation must be right. Okay? Okay. So that's that. I think we are done with this. The last bit here is work for you to try out. So here are 3 questions that I want you to try. Try to find the implied domain of these 3 functions. And once you're done with that, I want you to now think further and try these questions here. All right? You notice now of these 4 questions, you notice now we have, it's not just a reciprocal function, but there is a square root, and we discussed square root in video number 7. So think about what you understood from video number 7 and what we have understood from video number 8, this video, and then combine those to try and find the implied domain of these particular functions, okay? We will discuss your results once you've tried them yourself. Okay, the next video will be the solution of these particular questions. So these are now exact kind of questions that you might find in an IB diploma exam paper. All right, thank you very much. Meet you in the next video.